Okay, I'm going to be showing you light experiments. This is a photon, and that is from a red laser. But you see the black and the white particle back to back? Well, the green is the same thing, only it's much more powerful. You see, it's the identical same particle, no difference whatsoever. However, it is much more powerful, and I can prove that by showing the two of them going through the venturi at the same time. The red just gets pushed out of the way. The green has much more power and reconcusses way out here. So it's much more powerful, and the blue is much more powerful than the green. And I'll explain all these things. The blue is just comes through like a rocket ship, and you just barely can see that it's even two particles there. Now, we're going to go into this deeply, and get ready. Alright, just so you understand the starting point here. My point is that every single thing there is made out of that black and white particle. So green, red, blue, molecules, gases, 100% are made from those two particles. If we separate the black from the white, or green or red or blue or whatever color it was, is that white the same once it's apart from the other particle? Are all these electrons created equal? Or once they're propagated from green, does it have a certain value? If it's propagated from blue, does it have a certain value? If it's propagated from red, does it have a certain value? Because I can guarantee you red has very little energy compared to the green and the blue, especially compared to the blue. The blue is very, very powerful. And I have shown that by turning on LEDs with the blue laser, get a 2.5 volts. And the red won't turn on at all. You just shoot it right in there, absolutely nothing. The blue, 2.5 volts. This is what we want. We want to create voltage out of this. So we need a powerful laser, first of all. Then we need to restrict its entrance into this venturi, and that creates this pure white power. Now, is this power just as powerful as if it was green? Just as powerful as if it was blue? I don't know. I can tell you that there are two different energy values. I think I've shown it before. Here it is again. This is not anywhere near as powerful as the green when it comes in here. Once the white is apart from the red, is the white just as strong as the white of this one? I don't know. If they're both apart from their carrier particle, which is what they call them a carrier boson. That's the black one. The black one, well, it actually pushes the white. Watch, it actually pushes the white. See, the black one, and even when they're in their photon phase, like here, this is still they're still attached together here. They're still attached. Here's where they break apart right here. But all the way up to here, which is this is the unusual event. This is the things that they cannot do at CERN and Fermilab, and this is, they could do it, but I think they could do it. I mean, obviously they could do it, but they're not. And this is what we end up getting now, is this kind of energy. I think we got some serious energy here. Now, is that red, the white that creates this red, less energetic than the white that would create green? I think it must be. I don't know. I just don't know. I do not know. If once it's separated, I would have thought once it's separated completely, so the black and the white is together if it's a green, and it's going a certain spin. If it's a blue, it's going faster. If it's a red, it's going slower. But once they're broken apart, this should be just on its own. It shouldn't be spinning anymore, I would think. I don't know. Is it still continuing to spin? If it is, well, let's put it this way. This is what I'm trying to figure out. Is this value the same for blue, red, and green, or every color once it separates away from its other counterpart? Or is it based on its original color value, green or blue or red, or whatever color it was? And so far, I cannot tell. I don't know. Okay, my friends, it just gets deeper and deeper and deeper. Now, if you can separate these particles, the black from the white, is the white exactly the same energy value no matter whether it started from a green or a blue or a red? Because I'm showing you right now, this is green, this is a photon. This is red, this is a photon. If I separate that white completely away from that black, so the black has no influence on the white anymore, will that white be exactly the same value as if I separated the white from this black one and it started as green? Because this is much more energetic. There's no question about that. Now, what happens to the white? Does the white now become just a white by itself? And they're identical, even if it was a blue, it started a blue. You see how this comes in hot? It's just sizzling. And it slows down, but it's still really, really, really hot compared to the red. Will that white particle have the same value as the red if we separated it? This is my question, because here's the red separated from the white, and then the white came through and created the Higgs fields, and that looks to me like the other white. And well, let me show you the all right, you just saw the showers. All right, the black comes in, cannot get through, just pushes the white through. 100% white, not one single black one in here. And then they recombine out here, which is a distance away that this has spread out its compression enough where they can jump back in and reattach to the white, which is what they want to do, it appears to me. Now, so we just saw that separating, coming back together. Here's the green. Now that's coming straight at us. But you see the black one's going off to this side and the white one's going off to this side. Green's hard to control. It's not easy like the white. The white, we just a whole 100% white coming at us. That we have no problem with. The green sort of skirts off to one side, but there's zero white over here. I mean black. So it can obviously be separated. Now, is the black the same value as every other black? Is the white the same value as every other white? Once they're separated? That's got me confused. That's got me a smidge confused. All right, because they're showing the same thing. Now they have all the different colors. All right. You know, this is funny because this is a gamma ray burst, but it's also green, red, blue. Isn't that funny? And because at the end, they all the different colors come out here. Well, wait a minute, I got another one that shows all the different colors. But here we're coming through the Venturi. For some reason, it happens like a Venturi out there. Shoots out this cone. All that white is just pure white. Then you get the black line. Then you get the recombination. Exactly what I am showing here. Identical. No difference whatsoever. There's the ejection. Here's where the white starts, and then it starts to the black line, and then all of the particles come back together. Now here's where it shows the photon emissions. You know, they call this the prompted gamma ray emissions or whatever, and that's the exact same thing. Now they show all these different colors, and the reason they have all those different colors is because they have a lot of different particle sizes. They're starting with protons, I believe. This is in outer space somewhere, and they have no reason, no way to explain this, but they see it, and they say, well, this is what we see. And it's the same thing I'm showing. And at the end, we're showing this white field being pushed by the dark particles, exactly the same thing. Only we have just one color. Right, there's the dark particles pushing the white particles out. And I think this is good. It's absolutely interesting. And it shows that light spins in a circle. There's single slit, so it's not double slit. It's not flapping waves this way and that way. You know, it's pretty hard to believe what we've been led to believe, and believed it. If you can believe that. Okay, get ready, my friends. You're going to see all of this stuff in extremely great detail. But before I do that, I want to show you that these are the particles that we found doing these light acceleration experiments. And this is the two neutrinos, the muon and electron neutrino, turning into a regular muon and an electron shower, precisely as it is here. Prior to it crashing at the Venturi, the black and the white was attached together right here. And this is exactly what they found at Fermilab and CERN. And we're going to look at that right now. This is the Fermilab article showing the exact same particles. And then they're going to talk about the Standard Model being the most successful theory ever. I have to disagree and agree. Alright, I mostly disagree. At its core, it's totally wrong. The Standard Model consists of this. 12 particles, the smallest building blocks we've ever found. They are not, there's not 12. Where is it? Here it is right here. They say this is all the particles. There's only these two right here. That's the white one and that's the black one. And the two together make a gluon. Two gluons make a photon. Every other one is different upspins, downspins, different phases, different neutrino values, which is impact value. Every one of them is made of these two particles put together. That's all that exists, is those two, as far as I can determine. Alright, I just showed you. These are the smallest particles they've ever found. Fermilab, and here they are right there in our light. Now, normally they are in this configuration until they concuss and really literally explode. I mean, literally. That is a subatomic nuclear explosion right there. Absolutely phenomenal amount of energy, I think. And we need to look at this. Anytime you have this kind of luminosity, that's energy. And these are the two particles, a muon neutrino, electron neutrino, which come from light. Only they see it as showers coming off of their explosions of head-on stuff. We don't need that. We crush the fields into a Venturi. They couldn't no way they can get away from each other. So instead of hitting them head-on and hoping they're going to hit exactly, which they don't almost ever, we're forcing them to concuss through a Venturi. They can't get away from each other. They have to crush. Otherwise, they try to hit them head-on. They're crushing them, but not like we are. Much more better, much better. All right, here it is. That's it. That's the whole deal, and that's done with a couple of $100 worth of equipment. All right, you know how I'm always pointing to the luminosity and saying, look at the luminosity, that's how much energy? Well, that's because it is some energy. Luminosity is the amount of energy an object gives off per unit of time. The quantity is often in units of joules per second, otherwise known as watts. The same unit used in electric circuits, but in the form of radiation energy rather than electric power. We're taking that radiation, turning it into electric power, and it is the amount of energy. So we should have a lot of energy. We should be able to turn it into a lot of electric power. I got to tell you, I find this kind of funny. This is the most successful theory ever. Now, listen to this. It says the force particles are the photon, which is made up of two gluons, which are made up of the W and Z bosons. Here it is right there. Now, but now they're going with 12 particles. There's only two. The W and the Z boson together makes up a gluon. Two gluons together, back to back, because these are like little bar magnets, make up a photon. That's all there is. And then everything else is just spinning up or spinning down or doing other little pushing and shoving, where you get your neutrinos and so forth. But now they say there's 12 matter particles and 4 force-carrying particles. We can explain all the outcomes of all of our experimental data. We even understand in principle how to take these building blocks and reconstruct an entire universe. Let me tell you something. The standard model doesn't predict, they can't explain gravity. They can't explain gravity. They can't explain 90% of the mass of the universe. It just doesn't make sense. The standard model's not right. They don't know about that dark matter. They've lost it. They just never knew it was included with the white matter making up this particle. Basically, these are the two particles together that are the gluon. All right, so the W and Z boson together make up a gluon. Two gluons make up a photon. There it is right there. After that, everything else is just pushing and shoving and so forth, different energy values, different spin rates. That's all. All right, somebody asked about regulation and about where would we store it and how would we do this. Well, it could be carried around in something as basic as this, like a little lunchbox. And you'd have all your different outlets. You can select between 50 cycle, 60 cycle, AC, DC, USB charging, 120, 220, whatever it was. Whatever you want. It's just simple regulation. That's very simple. That's all done already. Everybody understands that, basically. Now, you could put this into a battery pack, too. So, of course, the battery pack is, they can store pretty good battery power in a pretty small amount of battery space, but you still have to, that's going to be something that's going to be additional to this. This inside of here would be a whole batch of these. And this is tiny. I mean, this is highly magnified. So you'd have lasers just blasting away and have receivers and like a wall of receivers here and just tons of them going all over. And then harvest that energy and then put it into your battery pack. Or just plug right into it. And I don't know how much energy this would make. This is all up in the air right now. But if it's up in the air, we should put it down on the ground and just see what we can make out of it. Because right now it's just, I'm going to tell you right now, there's zero question, zero, that this is an increase in energy. This is 100% less, well, I mean, I don't know how many percentage less. This is a small amount of energy compared to that. There's no question about it. Even the reverse EMF, the reverse electromotive force is just pushing back so hard against this that it's lighting up all these particles coming this way. They shouldn't light up this way. It's just, that's not the way it works. They usually light up coming this way because they're impacting with something. This is lighting up coming this way because these are impacting backwards. This is a whole new realm of physics. Boy, I gotta tell you, I was impressed with this article from Symmetry, Dimension of Particle Physics. Now, they're talking about what is a photon. This is my realm. This goes back to 2021. The fundamental particle of light is both ordinary and full of surprises. And it goes through, I mean, you can easily understand what they're talking about. And it's, they go right from the beginning of time. What was it, a wave? What was it, a particle? Is it a carrier? Is it a boson? Back to 1690, 1704 optics. I mean, this is very, very, very good. 1801, and they go right down the whole line. Who thought what? When? 1905, Einstein, Planck. Now, it keeps going and going and going, and they just really, nobody ever fully understood light because a lot of reasons. But anyway, now they're talking about gauge bosons. Now, they're talking about force-carrying particles. Yes, that's the gauge bosons. That's the black and the whites together. And it goes on and on and on. And then photons as a tool, and then photons remain important in physics. Then Donna Strickland won a share of the Nobel Prize in Physics in 2018. That's only a couple of years ago, for her work developing ultra-short, high-intensity laser pulses formed from highly focused, high-energy light. That's pretty similar to what we're doing. And they got the Nobel Prize for that. And they're talking about across the electromagnetic spectrum, photons can provide us with so much information about the world. Oh, photons are the only thing we have to sense the world. Photons not only are light, they're heat too. Photons send off heat. Anytime something glows, the more glow there is, the more heat's coming out of it, usually. Usually. But anyway, she got a Nobel Prize for this, working with ultra-short, high-intensity laser pulses. Boom, 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 boom. And using focused into high-energy light. I don't see where that's much different than what we're doing. All right, because these are all short pulses. Pop, 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 pop. And this is a construction laser. They use the pulses to check the distances. See, there's like the pulse, 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 pulse. And then when we put it through the Venturi, it accelerated it. So I'm not sure what they did, but I guess they're using it to etch glass and all kinds of stuff. So they're using it as a tool. This is what this should be. Somebody should look into it. I think we might be able to harvest this. If we could, I think I've shown this about a bazillion times, probably today as well. What we're getting is the energy right here. If we could get that and harvest it into a solar collector style device and slam it, bam, 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 down into our storage. And with a photodiode, it can't go back the other way. It's just going to be locked in there. And then in order to let it get back to the black, we have to make it go through our devices. That's what electricity is all about, keeping the white away. And the black is so attractive to the white that once we let it go through that conduit, which is a wire or whatever, it drives motors, it turns lights on, it does all the stuff that electricity does. And we could regulate it in any way we want. We could keep this laser going 24 hours a day. This just keeps running. And that's the output. And if there's excess energy here, we're golden. And boy, I'll tell you, there looks like more energy here for sure than there was back there, as far as I'm concerned. And there's nothing changed other than crushing the fields down into a tiny, tiny little tuned Venturi. That's all. We didn't add energy. We didn't do anything else other than force this stream of particles to crush themselves. Instead of hitting them head on, we're crushing them into each other. It's the same effect in the end.